Hello. Uh, just a sec. Yeah. Uh, Good evening to all. So today, I welcome you again. So today we are gonna we will revise the assignment one, and I hope you all know how to submit the assignment. Also, I'll show you once. Here. Uh, okay. So just a sec. Maybe you guys are not visible. Wait a minute. Yeah. So yeah, here if you go in the SWAM website, here you can go in the assignment one, and you just can submit it here. By adding the file, this is the assignment. And assignment I have already opened here. Sorry, it's not okay. Okay, this is the assignment, right? So this is the first assignment. So we have to submit it by tomorrow, 5th. So yeah, so today we are going to solve this assignment. Okay. So since I have to like write and show like I have to check the PDF also for the assignment and write it also. So I'll just shift it. I won't show this assignment many a times. I have already the assignment with me. So I'll just solve it simply. So from there only you can check, like cross check afterwards that which one was the question one or two. Okay. So I'll just directly go to that. Please let me know if my screen is visible because I can't see it. Is my screen visible? You can answer on the chat, or you can tell me also. If my screen visible, please let me know. I guess it's fixed now. So yeah. So the first question is find the susceptibility and relative permeability of an ideal superconductor. A paramagnetic material has a magnetic field intensity of 104 ampere per meter. You can also check on your own, what is the questions, so that you can trace me upon that. Okay. Sorry, just I'm admitting people are entering, so I'm just admitting them. So yeah. So we'll start with if the susceptibility of the material at room temperature is 3.7 into 10 to the power minus 5, and calculate the magnetization and flux density. So they are asking, right? Yeah. So what we should start with, see, magnetic susceptibility, we all know. So magnetic susceptibility, it basically describes how a material responds to a external magnetic field. This is question number one. Assignment one. Okay. Okay, okay. Sorry. Okay. I guess I'm audible now. Okay. So the first question is related to intense susceptibility and relative permeability of superconductor. Chi, it is the magnetic susceptibility. It is denoted as chi. It is basically how a material responds uh, to an external magnetic field, right? And for an ideal superconductor, as we already know that those are perfect perfect diamagnetism. Those show, and those has perfect Meissner effect. Also, they show Meissner effect means the ability to expel all the external magnetic field, right? So means how it is then responding to the external magnetic field, a superconductor, it's totally expelling. So for that, I'll just write it down. For a perfect superconductor, here it is mentioned in question one, ideal, the term, so I'm writing that only. Superconductor, I'll further write it as SC for superconductor. It is chi equals to -1, and the relative permeability, you are, yes. The screen is already being shared. Is everybody able to see, or like someone particular? Uh, so please like check your connection once, or we'll wait. You just rejoin, then maybe then you can see. So whoever can't see the screen, please refresh or rejoin, then maybe you can see the screen. I hope now everybody sees my screen, so I'll just continue. Um, So, and the relative permeability, the expression is given by 1 plus chi. So if we substitute the chi value of -1 for the ideal superconductor, it will be 0, right? 1 minus 1 equals to 0. So the question was, a paramagnetic material has like find the susceptibility and relative permeability for an ideal superconductor. So this is for 1A, we can say, like, though in the question it is not divided as ABC, but for our easiness we can do that. So the next sector is, a paramagnetic material has a magnetic field intensity of 104. So magnetic field intensity, we can write it as H. I'll just write the whole thing. Magnetic field intensity, H, equals to 104 ampere per meter, right? Yeah. Then if the susceptibility of the material at room temperature, chi at RT, it is 3.7 into 10 to the power minus 5, right? So calculate the magnetization and the flux density. And what is the magnetization? Magnetization is the chi into H, right? So, chi is given and H is also given. Means susceptibility into magnetic field intensity. So you can just multiply it simply. So I guess you can multiply it and you can detect the thing, right? So this will be done. Then the magnetization, this one is the magnetization. And also they have asked about flux density. So magnetic flux density next. Magnetic flux density. So magnetic flux density is B. We denote it as B. So B is mu 0 H plus M B. Right. So, yeah. So, so H plus M into B, this only the formula. And if we do, like, if we substitute, and also you already know that this one has value of 4 pi into 10 to the power H minus 7, right, of H. Now, if we, like, uh, sorry, this is, yeah. And if we substitute the values, already we know the values of M and H, then you can just simply detect the value of B, right? So basically B will be, I'll just write for your understanding, 4 pi into 10 to the power minus 7 into H plus M, right? Now you can detect the value. So the first question is done. Then the second question is, you can cross check, you can simultaneously cross check the questions. Okay, the second question is, using the semi-classical equation of motion in presence of the electric field and the magnetic field B and Faraday's law, the law is given below. Find expressions for E and B vectors in term of superconducting density of J. So first we'll know that what is the, like, they have given this expression F equals to M into dVs by dt. So here what are the, like, what does the terms explain? So this is like Newton's second law for superconducting electron, right? Now F is the, of course, force, you already know. F is the force of an force of force on the electron. Now what does that mean? It means it is the force that acts on a superconducting electron due to the external electric and magnetic field, the presence of the external electric and magnetic field that exerts a certain force on the superconducting electrons, that is represented by F. Now M is, of course, mass. M is mass of electron. Then Vs of course, velocity of the superconducting electrons. Like superconducting electrons means when they have already paired, like bound by Cooper pairs, right? Cooper pairs means two electrons, like excluding the Pauli's expansion principle, and they're attracting each other, and they have formed Cooper pairs, right? And in that, whatever the motion of they're gaining, that velocity is denoted as v here. Okay, and this is also the superfluid velocity, and dvs by dt. This is the derivative of the velocity, right? It represents derivative of velocity means what? If you go to your basic sciences, it means the acceleration, right? dv by dt. It is the basically derivative of velocity means acceleration of this superconducting electrons. Acceleration, okay. Now, next, also, uh, the next equation is given here is the curl of, from the question only it's given, I'm not making it, like curl and into curl of electric field equals to minus dB by dt. These are all vector terms. Now this is curl of electric field, we call it curl of electric field. This means how a electric field circulate around a changing magnetic field. How electric field, I am just writing as E. Um, it circulates or it revolves around circulate around changing magnetic field. Magnetic field, or B, I would write. Changing B. Now, dB by dt means derivative, like time derivative of that magnetic field, right? What does that mean? This is also means, this means, this means flux, right? So you know that if here the derivative or the time derivative of the velocity is the acceleration of the superconducting electrons, and here the time derivative of the magnetic field is the flux, right? So this is the basic terminologies you should know. Now coming back to the question, they have asked the find expressions for E and B. Now from here we can say that there is one equation of motion in the electric field. Equation of motion in an electromagnetic field. It is, you all, I guess you know this, m dv by dt equals to E plus Vs into V. All the terms I have explained, right? E is the electronic charge. You already know that. Uh, yeah, all the terms are explained. Now Vs into B, the term separately you know, but this means this is the Lorentz force term. Like separately you know, right? Vs, what is Vs velocity and what is BB, chain magnetic field. And together the the dot sorry, this is not dot product, this is cross product. So this cross product means Lorentz force term. Lorentz force. It represents the force experienced by this moving superconducting electron due to the magnetic field. B is present means due to the magnetic field. Here I am writing uh, velocity into magnetic field means into, if this is not simple into, this is cross product. This means, I am writing here, this means force experienced by a superconducting electron due to the presence of magnetic field. Okay. So, yeah. And there is one more equation, London's equation. London's equation that relates the current density and to velocity, right? Into VS. This is already in the question. It's mentioned it is the supercurrent density. Means it is the current density carried by the superconducting electrons. Those are already in Cooper pairs, right? And NS is the density of Cooper pairs. Density of Cooper pair electrons or superconducting electrons. Or superconducting electrons, yeah. Someone has just got entered, so I was admitting him or her. Now E is the charge and V is the velocity, you already know. Now this equation, what does it tell? This tells that the supercurrent density or the supercurrent density, this term already mentioned in the question, is related to the velocity by the superconducting charge carriers. So means this is the term there, like routing to. Now, the time derivative of this supercurrent density, if we do derivative of this J term, so dgs by dt, it would be n e square s by m e. Okay, I will explain. So, the dgs by dt, the derivative term means like with respect to time, how the flux density or the supercurrent density is changing, right? Now, n e square by m, this term is the London parameter. This is a constant. It relates that how electric field is revolving around the changing supercurrent density. All right, change in electric field with respect to changing supercurrent density. Now this equation, this whole equation tells that with an applied electric field, the supercurrent density, like it responses with respect to the like changing what's a J's is the supercurrent density. Means the supercurrent density is dependent on the an applied electric field. Okay. Now this electric field terms is also like we can just reverse this, like taking the LHS to the RHS and RHS to the LHS. Or this equation only we can write as E equals to m by, just do the opposite, n a square djs by dt, right? Now this is the same meaning it holds only. Now if we apply the Faraday's law, where I have written this one, no? This one, the Faraday's law. It's already told in the question. So yeah, if we apply the Faraday's law, so Faraday's law tells that how electric field circulates around the changing magnetic field, right? Now London's second equation is coming in the picture now. London's second equation. You see how beautifully these equations are like related to each other. Into B equals to B lambda square. Okay, so this one is the Laplacian. Laplacian of B means the magnetic field. So this represents how the magnetic fields varies, especially inside the superconducting material. And B is the magnetic field inside the superconductor. Magnetic field inside the superconductor, and lambda here Lambda is the penetrating depth that we have already discussed that before explaining all the external magnetic fields. A superconductor, a certain amount of magnetic field inserts into the superconducting material, and the that depth is we can call as penetration depth, right? This is the characteristic length basically. After that, the magnetic field totally got vanishes or decays, right? Yeah, this is related to the Meissner effect. So basically in the question they have asked this much only, कि find expressions for E and B vectors in terms of supercurrent density. So in terms of supercurrent density, so I'll just write clearly once. So this one you can write as a um like a for the electric field, relation between electric field and supercurrent density, right? And this one as the magnetic field. I think you should have derived the whole thing as I have like written here. Though this PDF, I'll make this PDF and I'll upload. You can just after this class you can just go and check and you can understand better. Okay. Okay. So moving to the next question, it's about the Gibbs free energy. Yeah, Gibbs free energy. The question is the energy given, formula is given. Okay. So the formula is given in the question only. It is written as G equals to U minus Ts minus nu 0 Hn. And it is written symbols have usual meaning, also assume that G in this normal state is unaffected by the magnetic field. That is, this equation is also given Gn T 0. And though it's written usual meaning, but I'll just explain for your understanding that G, you know that it gives free energy, and from thermodynamics, you know that G means like for equilibrium, you should have a minimal of Gibbs free energy, right? And this is not V, this is U. So U is the internal energy, right? Internal energy. So this is the total energy conserved by the system. This includes all the kinetic and potential energy of all the electrons and phonons. And T is the temperature and absolute temperature rather, and S is the entropy. So it is basically the disorder. S equals to entropy, basically the disorder, right? Disorder present in the system. So a superconducting state should have a lower entropy than the normal state. Means then only it will get it will get less Gibbs energy, and it will be more stabilizing. Like it will be more ordered then. Not we don't want a disordered superconducting state. So lesser S value, it will be more stabilizing the superconducting state. Now here mu zero mu zero. This one is the permeability of free space. And this is we have already done previously. Okay. And this tells that permeability means how a magnetic field interacts with like in the free space. Now, uh, yeah. Um, and then the H terms, H you already know, external magnetic field. You can just write external magnetic field. External magnetic field in the system. Like on it in that in this term, the magnetization and the energy difference between the normal and superconducting state you can like analyze. Now M is the magnetization. Yes. Huh. Huh. हाँ, हाँ, मैं एक बार दिखाती हूँ। Like after this class, I'll just like exchange my screen. I'll show. Okay? क्योंकि बीच में करती हूँ ना तो वो थोड़ा गड़बड़ होता है. Okay? Ah, no, no, fine. It's fine. You can ask. So I'll just show after this class once this like there are six questions in the first PDF. So I'll just finish all of them. Then I'll like show that where I'm going to upload. Okay? Huh, okay. So yeah, aim is the magnetization, and this means the response of the material to the applied magnetic field. Now in a superconductor, you already know it shows a Mason's effect, and that leads to perfect diamagnetism. Means for a superconductor, m equals to minus h by nu naught. So from here also you can show one relation, right? So and the question they have asked that find an expression for the change in G, that is del G. They have asked like find an expression for del G between the normal and superconducting states in terms of critical magnetic field Hc. Means some del G should be some function of Hc. This is we have to detect. Right. Now already this equation is given. So from here we can say that Gn. Okay, this one I am just describing the term. Gn means n for normal state. So gives free energy in the normal state. Okay, so this free energy is not for superconducting state. This is for normal state. So it doesn't directly depend on the external magnetic field. Okay, so that's now. Yeah, and for the superconducting state, we can then write the symbol as Gs. So we can also from this equation, we can take as Gs equals to, sorry, Gs depending upon T and H. H means external magnetic field. We can write it as Gs, T and 0. When external, there is no external magnetic, what exactly happens inside the superconductor. Now, so this the free energy of this superconducting state Gs, it is lower than the Gn by an amount of, this means, so Gs minus, okay, I'll just write Gs minus Gn equals to del G, right? Del G they have asked to detect. It is by minus Hc square divided by 2 mu naught. Hc, they have already told that it is critical magnetic field at which magnetic field the superconductivity is like totally gets destroyed. Means above Hc, the superconducting state will go back to its normal state. Now Hc by 2 mu square, this means the, yeah, the energy gained by the super by becoming the superconducting from normal state is the reduction of energy due to the formation of the superconducting state. Means here we can show that, see, it is negative also in it has a negative symbol, so we can say that this is more stable, it has lower gives free energy, right? So yeah, so basically this amount, this Hc square to nu 0, this is the extra energy which superconductor like possess, or it stores. Okay, so I guess this was the question only. Yeah, like this was the question only. Find an expression they told. So this would be the expression. This one. Then the next question is, okay, fourth thing. The critical field of niobium is of 10 to the power 5 ampere per meter at T equals to 8K. Means critical field Hc by T we write no. So here we will write for niobium Hc at 8 Kelvin. It is 10 to the power 5 ampere per meter. Yeah, now it is telling the and is double of that at T equals to 0 means Hc of T equals to 0 means 0 Kelvin equals to someone wants to say something. Somebody is coming like joining now. Yeah. So yeah, they have told that at the T equals to 0, find the transition temperature of niobium. So you already know that here it is 2 into 10 to the power 5. So there is one expression Hc by T into Hc at 0 minus, sorry, 1 minus, 1 minus T by Tc whole square. So you already know they have asked find the transition temperature means Tc you have to detect. So I guess it will be easy for you. From this expression you can just detect or 1 minus T square by Tc square equals to Hc T by Hc0 means 10 to the power 5 divided by 2 into 10 to the power 5. Then this is 0.5. Then T square by Tc square equals to 1 minus 0.5 means 0.5 and T is 8, right? 8 square divided by Tc square equals to 0.5. Then Tc square equals to 8 8 is 64. So I'll just write 8 square by 0.5. Then Tc you can detect. Right. So it was just simple like equation only. Now the second one is draw internal versus external field for a type 1 and type 2 superconductor. So you already know in the last class we have seen that here H is 0 and here it is B equals to 0 for type 1 since it has only one type of critical magnetic field for type 1 superconductor and for type 2 there are two, right? Hc1 and Hc2. So this is a mixed or vortex state where how it forms? It forms as in it forms as in um, like when like for type 2 superconductor it allows the external magnetic field to penetrate a little bit and that region is become the mixed or vortex state and above that like here B equals to total 0 means the no external magnetic field is there means totally expelled similar to the type 1. So this region is similar to the type 1 and the above that is the mixed state and but above the Hc2 it becomes to the normal state. Okay, so this one the earlier class only we did this one from the earlier class and then the C question. Consider the ratio of kappa equals to lambda by zeta and where k is the penetration depth and this one is the coherence length and what is the approximate value of Kc that differentiates type 1 and type 2. Okay, that is 1 by root 2. No? 1 by root 2 is the value. So below, when kappa value is below 1 by root 2, it is type 1. Sir has mentioned this in one class. And when it is 1 by root 2, like above, then it is type 2 superconductor. This much only you have to write. Then the fifth question, the fifth A, derive equations of coherence length of superconductors using the Heisenberg uncertainty principle. So yeah, so the coherence length, this we can tell, this is the characteristic distance from which, like over which copper pairs remain correlated in a superconductor, right? The coherence length. So Heisenberg's coherence length. Heisenberg's uncertainty principle, from there they have told to derive Heisenberg's uncertainty principle. So this tells del x into del p equals to z. Right. So del x means uncertainty in position, and del p means uncertainty in momentum. And this one is the reduced Planck constant. And this means h by 2 pi, right? And h value we already know, h by 2 pi. So yeah. And what are they? Anything else? No, they have just asked to derive this value taking help of this Heisenberg's uncertainty principle. Okay. So yeah. So del P, the uncertainty in the momentum, we can write it as momentum means what? Mass into velocity. Right. Yeah. Somebody just entered. So mass into velocity, mass means electrons mass, and v is the velocity, like the Fermi velocity. Since superconducting electrons, as you if you remember, superconducting electrons are those are present like in vicinity of the Fermi surface. So that's why we are like writing as a subscript of F, like the those specific Fermi electrons only. Like the so we can tell it this as a Fermi velocity, and this formula is the basic plus two like from plus 2 we are learning that momentum equals to mass into velocity, right? Now with coherence length, the formula with coherence length, it is h by mvf, right? Means h by del p. Now there is a bcs BCS theory, right? So from the BCS approximation, we can take that from the BCS theory. We know that the energy gap del, this also plays to determine this coherence length. So this is the energy gap, superconducting energy gap. Pi is the pi, and VF, and this one is you already know means H by HVF by 2 pi square. It will be into del, right? So if you want to like interpret what does the like what does physically the coherence length means, I've already told that within a certain distance, the external field can penetrate inside the superconductor, right? So this coherence length is also means the size of Cooper pairs. Right. So it determines that how superconductivity varies. For type 1 superconductors, coherence length is large. For type 2 superconductors, coherence length is small. Okay, and due to the penetration depth. Um, In the question, basically, they have asked that derive the expression. So this expression is enough. Like nothing to, like no numerical question is there. Like just derive the equation, and from the equation only you can derive. Okay, now the second 5B question is uh, calculate the critical current and current density for a wire of a lead having a diameter of 1 millimeter at 4.2 Kelvin. Okay, current density, critical current density is IC, we write. Current is I, and for critical it's C subscript. Critical current density, right? It's basically the current density, that means the maximum current a superconductor can carry before like going back to its normal state. Maximum current carried by a superconductor before transitioning to its normal state. So they have given wire diameter equals to 1 millimeter. 1 millimeter, temperature at equals to 4.2 Kelvin, and critical field they have given 6.5 6.5 into 104 ampere per meter. And this critical current density, so how they relate? So yeah, there is one also that critical temperature they have also given 7.18. Okay, so how they relate this critical current density and critical field, magnetic field? It is it relates with the London penetration depth, that the lambda one. So this critical current density we also write as JC into this. Okay, this I have written mistakenly. Critical current. Yeah, this is not current density. JC, this one is the critical current density. So, critical current density is this one, JC, and HC is the critical magnetic field, and lambda is the London penetration depth. This is the London penetration depth, means the certain length over which the magnetic field decays in a superconductor, or it got totally expelled. Now, uh, IC equals to JC into A. A means cross sectional area. A means cross sectional area. So now you can know that wire diameter is gonna help us. Right. Is there anything they have right? Yeah, they have not mentioned anything. So we can think that superconducting wire, it is cylindrical. Means generally we draw superconducting material like this. So if we think it is a cylindrical, then its cross-sectional area would be pi d square by 4. D is the diameter, means r by 2, means yeah, sorry, diameter only given, so we can directly put. So pi into 1 square by 4 would be millimeter square. Please no, like be careful to the units. So this is by pi by 4 millimeter square. Right. Now I see. Also for IC we need JC value, right? So JC would be HC by lambda. HC value is given 6.5 into 1 10 to the power 4. I guess this is they have written like that. I guess it will be 10 to the power 4 because 104. Why should they write like this? 6.5 into 104. This is 10 to the power 4 should be. Yeah. So 6.5, yeah, and this is for they have not mentioned. Mm, okay, lambda value they have not mentioned. In material they have mentioned lead. Lead they have mentioned, no. So hello, yes. 2 pi r into x. IC equals to 2 pi r into xc. Like what will be the x? Actually, I am taking this equations. That's how, like, we know that the values, like, what are the given values? Say, IC, we can current, we can derive by the from the critical current density, right? IC equals to basically JC into A, right? I have written here JC into A. A we can derive from the diameter, and JC we can derive from here. For lead, the from lead this London penetration depth is given. So from that value we can just like calculate easily. You can take other expressions, not a problem at all, but we should know the values. That's why like this values are given. This values are given from the question only, and whatever this value is known from the literature. So and this expression also is known from the like from school level. So I am taking these expressions. Okay. So as I have already told that IC, what is the physical meaning of IC? IC means the critical current means the maximum current carried by a superconductor before it goes back to its normal state. Now, if I become like I is larger than the IC, then the superconducting state will be destroyed. Means the material like totally it goes back to its normal state. So this is very helpful. This information is very helpful for designing a superconducting magnets and like superconducting magnets. Where do we generally use? We use for them as in MRI scans, then NMR machines and all. Then of course earlier like last class I have mentioned about maglev trends. So those things, and for power grids also, power applications. Then like refrigerator and all, they are also they have been using. So yeah, that was the thing. And the last question is, how does the isotope effect? How does the isotope effect indicate phonon mediated pairing of electrons that causes superconductivity? So the isotope effect, I was telling last class, isotope effect. It states that Tc equals to m minus alpha Tc. Right? M is the mass. So the mass of the isotope here we you can put, and from this what are you like what are you going to learn? Yeah, how does the isotope indicate phonon mediated? Yeah, let me just do one thing. Yeah, so this suggests that where and yeah, and for alpha equals to, we know that it's zero point 0.5 value. It's just a constant, and Tc is the transition temperature, and m is the mass of the isotope. So Yeah, so from this equation, you can tell that the isotope effect indicates that the phonon-mediated pairing of electrons that causes the superconduction at a certain temperature, that is the Tc, and the relation is such as the Tc value is and the relation such as the Tc value is directly dependent on the mass of the isotope. Like whichever will be the lighter isotope will have the higher value of the Tc. And phonons, of course, phonon mediated pairing of electrons means Cooper pair formation is enhancing, means ultimately the superconductivity is going to increase. And the next question is put usual values of M, C, E, and N. What is lambda L? What is the temperature dependence of the penetration depth? Okay. Using lambda L, you can say M into mu 0 into N E square. N value is given. N equals to 10 to the power 22 per semi square. And yeah, and they have told that E square is the electronic charge and mu is the like permeability and M is the mass. You already know, right? So they have asked put the usual values and sorry, what is the temperature dependence of the penetration depth? So basically, we have to do the derivative, right? Um, just excuse me for a second. My pen is not working. Just hold for a second. Okay, in the meantime, if my pen is not working, in the meantime I can show you that how the you have to submit the assignment. Yeah. So here, okay, I have to open that online course. Yeah, so you are going to, I have already shown that you are going to submit your assignments here by going here, assignment, go to assignment and add file, whatever the document for you have prepared, you'll submit there. And the last here, it is a problem solving session. In the left hand side only you'll find. Then here, like like click in on the problem solving session recording and click here. Then again click. Yeah. So here I'm going to upload the YouTube link, and here in this presentation folder link I'm going to like accumulate all the lectures, like the last one also, and this one also. Okay. So from there you can like have a look on that. So once this is done, so this is already 8 for 15. So I'll by 9 I'll upload, and you can check after your dinner, whatever. Okay. So yeah, so we are on that last question, right? So I'll just share once again the screen. So yeah, so the question was the lambda. We have to detect the lambda L. What is lambda L? Lambda L, we have already defined lambda L before only. It is the penetration depth, right? So what is the temperature dependence of that penetration depth? So lambda L is basically, so from this, like they have told, give with the function of you have to derive it, like taking all these terms together. So lambda L is m star mu 0 n e square. Simple. So m is the mass, then e is the charge, you already know, and n is the superfluid density, which is already given the value. This one the value is given, right? And mass of electron and electron ka charge, you know already. So if we do that, then the derivative of this, uh, but also there is one term which is b. B we know, if we know, if b equals to, we can write it as just x by lambda l plus b2 by the minus x by lambda l. From here also we can derive. Actually, I have to look into this question. I'll just solve this and I'll upload this together. Okay. If you have any other question, you can ask. Or if you don't have any other question, you can look into this PDF or the YouTube video later on, and you can just understand there that then only. Yes. This is 10 to the power 4. This is 10 to the power 4. It should be. Ha ha ha. Like earlier, I was also taking it as a 104, but when I came here, then I saw that they like one won't write as 6.6.5 into 10, 1 not 4. It should be 10 to the power 4. Okay. Yes. Okay. Okay. Actually, I have only like for myself also I am doing the assignment, so I've only looked up on the first assignment only. So second assignment. Okay, which question you need? Like, like if you have any particular question. Third one and fifth one. Actually, earlier they used to do like a week wise. They used to like submit, like make us submit assignments. But this time I'm seeing that all together once they have put the deadline. So it's very difficult to. Uh, but all for all 3 weeks, all three assignments, no? Okay, third one is still time, but yeah, earlier also I took class on NPTEL, but that time they used to give like 1 week time. Okay, so the question you are asking about this homework two, for which questions? Uh, Third one and fifth one. Okay, actually I have not looked into this. I'll just look into these questions and I'll include in this PDF only by tonight and I'll upload. Okay, can you just check then? Like because I also have to look into these questions. Okay, by tonight I'll do. You just check tomorrow morning or whenever you have time, then you upload. Okay. I'm from IIT Hyderabad. I'm, thank you so much. If anyone else has any questions, they can ask or you can leave also. If there is no other question, I'll just add those two questions that was asked in this PDF and this question also from this home assignment one. I'll solve it and I'll upload. And by tonight, I'll upload in that Google Sheet and you can go back and check. Okay. Thank you all for joining. Good night. Thank you. Yes.